Hello, my name is Casey Shibler and I'm doing a reassessment on magnetic forces. The problem I've chosen is problem 69. It says in the following figure, the loop is equal to 15 centimeters long, or the loop of wire, the length is equal to 15 centimeters long. The height is 3 centimeters and it has a resistance of 0.3 ohms. It moves at a constant speed of 8 meters per second to the right, and it is emerging from a rectangular region where there is a uniform magnetic field into a region where the magnetic field is negligibly small. It says in the region of the magnetic field points into the page, and its magnitude is B equals 1.2 Tesla. So the first question asks, on the diagram, show the approximate charge distribution on the moving loop. Alrighty. I've actually shown it over here. I tried to fit it on there, but it just looks way too busy. So I put the charge distribution to be negative on the bottom and positive on the top because the magnetic field is going into the page instead of out. If it were going out, then we'd have an electric field up and the charges would be reversed. But in this case, we have one going in and the electric field is going down. So therefore, the negative charges are on the bottom and the positive are on the top. Alrighty, so then we move on to part B. What are the direction and magnitude of the conventional current of the loop? Well, the direction of the current is going to be going clockwise because according to the right-hand rule, we have a current going into the page and we have a magnetic field going into the page and your fingers will curve in the direction of the current. So that's going around that way. To find the magnitude of the current I, we know that I is equal to delta V over R. We've been given R, which is 0.3 ohms. However, delta V still needs to be solved for. We do know that delta V is equal to the velocity times the magnitude of the magnetic field times the height. So whenever we plug all of these in, you'll see that we have I equals VBH over R is equal to 8 meters per second, 1.2 Tesla times 0.03 meters, which gives us 0.3 ohms over 0.3 ohms, which gives us I equals 0.96 amps. The next question asks, which of the following is true? The magnetic force only stretches the loop. The net magnetic force on the loop is 0. 1 is false. The magnetic force does not stretch the loop. That's more of an EMF deal. 2 says, because a current flows in the loop, there is a magnetic force on the loop. That's true. Awesome. And then 3, the magnetic force on the loop is in the same direction as the velocity of the loop. No. The magnetic force is not in the direction of the velocity, actually. So then we can move on to D, where it says, what are the direction and magnitude of the force that you have to apply in order to make a loop move at its constant speed? Well, if I take a look in my notes, you'll see that the magnetic force on a current carrying wire is equal to F equals I times L cross B. So using that equation, we have F equals I times L cross B. Since I is going up, the force will be directed to the left. So basically, as you can see, I is going up, the force is to the left. Therefore, we need to apply a force to the right if we want to keep this thing going. So once we apply it to the right, we can then plug in our values to get the magnitude because we've already gotten the direction. And that's 0.96 amps times 0.03 meters times 1.2 Tesla sine 90. As you can see, 90 degrees. You knew that. And that gives us 3.45 times 10 to the negative 5th newtons. Thank you so much.